Alright, the last topic for today is geometric sequences and series. I suspect that once you're comfortable with this, it will feel relatively straightforward because there's basically just one formula that you're going to be using whenever you start to sum up geometric series. But I will say that there are a lot of letters flying around in this section, so it's pretty abstract. I might encourage you to watch this video and then return to it after you've seen the hands-on example videos, because I'm mostly going to deal in the abstract. But it might be good for you to come back and review this once you're a little more comfortable with it. But here's sort of an overview for geometric sequences and series. A geometric sequence is a sequence where you get the next term by just taking the current term and multiplying by some number r. And that's how you generate all of the next terms. So if you want the next term, you multiply by r. If you want the next term after that, you multiply by r. If you want the next term after that, you multiply by r, and so on, where r is some real number. So for example, a sub n is equal to 2 to the n. That would be a geometric sequence, because if you want to get a sub n plus 1, that would be 2 to the n plus 1 power, and that is just 2 times the previous term. Right, so in other words, to get the next term in this sequence, you're always just taking the previous term and multiplying by 2. So the sequence here would be something like, I guess the first term is 2, the second term is 4, the third term is 8, and so on. And notice that to get from one term to the next, you're always just multiplying by 2. So this is a geometric series with common ratio 2. In other words, you multiply by 2 every time you want to take a step forward. So notice that if the next term in the sequence is given by r times the previous term, if you divide both sides of this equation by a sub n, then you get that the ratio between the next term and the current term is always going to equal r. So that gives us a way of deciding what that value for r is going to be if I just give you a sequence and I ask you if it's geometric. It also lets us determine whether a sequence is geometric. So if I give you a sequence like this, where the first term is 2, the next term is 4, the next term is 12, and so on, then I could try to figure out whether that's geometric by just taking these ratios and seeing if they're all the same value r. In other words, are we always multiplying by the same number to get to the next step? So if I take a2 and divide by a1, so that would be 4 divided by 2, then I get 2. So the thing that you had to multiply by to go from here to here is a times 2. If I take the ratio of these next two, so if I take the 12 over 14, that has a ratio of 3, so we had to multiply by 3 to get to the next step. And that means this is not a geometric series, because in a geometric series, you're always just multiplying by the same number over and over. So you would just be multiplying by 2 and then multiplying by 2 and so on to keep taking steps forward. So this one is not geometric. But in general, a geometric series is going to look something like this. It'll be the first term times that ratio r to the n minus first power. So you can normally detect a geometric sequence by just looking for a power of n or n minus 1 somewhere. So for example, in this sequence with b sub n defined by 7 over 2 to the n, I could factor out a 7/2 from this, and I would get that it's 7/2 times 1/2 to the n minus first power, and therefore I have written it like the above. So the first term in this sequence would be 7/2. If you just plug in n equals 1 here, you would get 7/2. And then after that, to get the next term in the sequence, you're always just multiplying by 1/2. So this would be geometric with b1 is equal to 7/2 and r is equal to 1/2. And maybe it would be good for us just to generate a couple of examples just so that you can see. So the first term would be plugging in n equals 1 here. So that would be 7 over 2. If I want the second term, I'm plugging in n equals 2 here. So that would be a 7 over 2 squared, which would be 7/4. If I want b3, I would be plugging in n equals 3. So that would be a 7 over 2 cubed, which is a 7/8. And notice that to get from here to here, or to get from here to here, I just have to multiply by 1/2. So at each stage, I'm multiplying by 1/2 to get to the next step. And that means that this is geometric with the first term equal to 7/2 and the common ratio equal to 1/2. This common ratio is what you multiply by to get to the next step. Another example is this one. So if a sub n is equal to 3 to the n over 2, then again, just look for something that's being raised to the nth power or to the n minus first power. That's usually what you're multiplying by to get to the next step. So this one would be geometric with the first term equal to 3/2. You can get that by just plugging in n equals 1 here. And then from then on, anytime you want to take a step forward, because of this power of n, anytime you increase that by 1, you're basically just multiplying the previous term by 3. So this would have a common ratio of 3. For geometric series, remember that a series is just a sum of a sequence. So the only difference between a sequence and a series is that in a series, you have some sequence, but you're adding it all up. So a series is just adding everything up. And before we talk about how to add up a geometric series, I need to show you one formula that we're going to use here. So note that if you take this expression, it actually will reduce to 1 minus r to the n. So this is 1 minus r times an increasing set of powers of r that I'm adding up. So in a geometric series, we're going to want to add up an increasing sequence of powers of r. So I would like a nicer expression for this circled thing. So notice that if I multiply this circled thing by 1 minus r, then if I distribute the 1 everywhere, then I'm just going to get all of this, right? So distributing the 1 would give me this. If instead I distribute the minus r to everything, then that first term would be a negative r, the next term would be a negative r squared, the next term would be negative r cubed, and so on. And then the very last term here is going to be a negative r times an r to the n minus 1. That would just be negative r to the n. In other words, you're adding 1 to this exponent because you're multiplying by r. And now notice that a lot of these terms cancel. So you have a plus r and a minus r. You have a plus r squared and a minus r squared, and so on. And actually everything cancels except for the first and last terms, because there's a positive 1 that's not canceled by the minus r's, and there's a negative r to the n that's not canceled by the positive stuff. So that means that this actually simplifies to be 1 minus r to the n. And that's really nice because if you divide both sides of this original equation by 1 minus r, so if I take this and divide this side by 1 minus r and I divide this side by 1 minus r, then clearly on the left side those 1 minus r's are going to cancel, and I'll just get this sum that we wanted to work with. And on the right side, we just end up getting 1 minus r to the n over 1 minus r. So if you ever have to add up a bunch of powers of something, so 1 plus r squared plus r cubed plus, all the way up to something, then this is just going to equal 1 minus r to the nth power divided by 1 minus r. So that's a nice way to compute the sum that we had here. And since a geometric sequence looks like this, so you just start with a1 and then for all of the subsequent steps you multiply by r, the geometric series is going to look like this. So here I'm going to use s sub n to mean the sum of the first n things in that sequence, and n is going to be the number of terms. So this lowercase n now is going to represent the number of terms that I want to add up, and Sn is going to be the sum of those n terms. So this stands for the series that corresponds to this geometric sequence Ai. Sometimes Sn is called the nth partial sum, so you might also see that terminology. But it just means add up the first n things. So if we're talking about a geometric series, or sequence rather, like this, and I want to add all of those up, then that means that the first term is a1, the second term is going to be a1 times r. To get to the next term, I would just multiply that previous term by another r. To get to the next term, I would multiply the previous term by another r, and so on. And you would do this all the way down to an, which is a1 times r to the n minus 1. So this is just me rewriting that original sum. This is the sum of the first n terms in a geometric sequence. Notice that all of these have a common factor of a1, so if I factor out an a1 from everything here, then the remaining part would just be a1 plus r squared plus r cubed, all the way up to the n minus first power of r. And we already saw that if you have to add up a bunch of powers like this, there's a convenient short way to do it, which is to just write it as 1 minus r to the n divided by 1 minus r. So this tells me that if I need to add up the first n terms in a geometric sequence, there's a shorthand for it. It's just going to be that first term times 1 minus r to the n divided by 1 minus r. So that's a formula that you'll see a lot. So if you need to add up the first n terms of some geometric sequence, then you can do that by just taking the first term times 1 minus r to the n divided by 1 minus r. So again, I know that there are a lot of variables flying around. I expect that this is pretty abstract for you, but you'll see several examples that are hands-on, and hopefully then you'll get a little more comfortable with the formula. But there's one last thing that I want to say in the abstract before ending the video, which is that if you wanted to add up infinitely many terms, so let's say that this n, rather than adding up like 7, let's say that you want that to be infinite, so that we add up infinitely many terms in this geometric sequence, then you need r to be smaller than 1 for reasons that you'll see in maybe a calculus class. And as n goes up to infinity, if r is smaller than 1, then that r to the n term that we have in this formula is going to get really, really small. So imagine, let's just do an example where maybe r is equal to 1/2. If r is equal to 1/2, and we're considering r to the nth power, where n is really, really big, then this would be something like 1/2 to the, 1 million. And if you plug in something like 1/2 to the 1 millionth power, this is going to be basically 0. It's very close to 0, because you're dividing by 2 1 million times. Right, so this gets closer and closer to 0 as long as the absolute value of r is smaller than 1. And what that means is that if n is infinity, so if you imagine replacing that n with infinity and adding up infinitely many terms, then you get basically the same formula as up top, except that this minus r to the n term is going to become a 0. So you can think of this, because r to the n is going to go towards 0, you can think of this as something like a 1 minus 0 up top, but normally you would just write that as a 1. So this is the formula that you use if you're trying to add up infinitely many terms from a geometric sequence. So let me give you an example here. Let's say that I wanted you to compute the sum from k equals 1 up to infinity of 1 over 2 to the k. So I notice that these are basically powers of 1/2. And therefore this is going to be geometric, because to get to the next term after the first term, you're just going to be multiplying by 1/2 over and over. So this is geometric with the first term equal to 1/2. You can just plug in 1 here to see what the first term in the sequence is. And r is equal to 1/2. To get to the next term, you're always going to multiply by 1/2. And if you're confused about this, you can always just check what a few of the sequence members are. So if you take this circled expression and plug in 1 or 2 or 3 and so on, you would get that the first term is 1/2, a 2 is going to be 1/4, a 3 is going to be 1/8, and so on. And notice that to get to the next term, you're always just multiplying by 1/2. So this is geometric with a 1 equal to 1/2 and r is equal to 1/2. And therefore, if I wanted to sum up all of these, so if I wanted to compute this sum, I could use this formula up here, which says that the sum of a geometric sequence is going to be this expression, a1 times 1 over 1 minus r. So the sum that I'm trying to work with is equal to a1 times 1 over 1 minus r by that formula up at the top. And now I can easily compute this sum using this formula, because this formula doesn't require me to add up anything. I just have to plug in a1 and r. So this A1 is going to go here, R is going to go down here. That in this case they happen to be the same, but they're not always going to be the same. So A1 goes outside, R is going to go down here in the denominator, and I would get that this infinite sum is equal to 1/2 times 1 over 1 minus 1/2. Let's go ahead and simplify that to end the video. So we'll have a 1/2 times a 1 over this denominator, 1 minus 1/2 is going to simplify to be 1/2. So we simplified the denominator there, 1 minus 1/2 is going to become a 1/2. This is 1/2 times the reciprocal of 1/2, or I guess if you'd like, you could just immediately cancel these. So this is 1/2 times 1 over 1/2. These should cancel, and you'll be left with 1. But you could also rewrite this as a 1/2 times a 2 over 1, and then cancel that way. But either way, you should end up getting that this sum is equal to 1. So the sum from k equals 1 to infinity of 1 over 2 to the k is equal to 1. This is the sum that we actually computed at the end of the last video, the last summary video, because I justified it by showing a picture. So this was the sum from k equals 1 to infinity of 1 over 2 to the k is 1/2 plus 1/4 plus 1/8 plus 1/16 and so on. So you're just adding up reciprocals of powers of 2. And remember that what we saw is that if you take 1/2 plus 1/4 plus 1/8 plus 1/16 and so on, you're just adding up half of what remains from this whole pi. And at the end, if you imagine doing this infinitely many times, you'll get arbitrarily close to 1. In other words, you'll complete that circle, and therefore you'll get 1 as your answer here. But normally, whenever you're summing up geometric series, you're not going to try using some sort of a picture to justify things. Instead, you can just use the formula that I showed you here. Okay, so maybe come back to this video and watch it one more time after you've seen the hands-on examples. But here I just tried to justify where these formulas are coming from, and hopefully the hands-on examples will make this feel a little more concrete to you.